Hello and welcome to, I believe, the last set of notes regarding bonding, looking at intermolecular forces. So, some vocabulary to look at quickly. We have intramolecular forces. Now, these forces are used holding atoms together inside a molecular compound. So, down here at the bottom, our intramolecular force is between two atoms that are sharing the electrons. We look at these with ionic forces as well as covalent forces. Our purposes today, though, is intermolecular forces. So the attractions or repulsions between neighboring molecules. That's this guy right here, from one HCl to another HCl molecule. Between each molecule is an intermolecular force. Any questions on the differences? Okay. So, types of IMFs, we like to call them. So, our intermolecular forces between neighboring atoms. Again, we are looking at one molecule or atom to another. The weakest are London dispersion, followed by dipole-dipole forces, and then the strongest IMF is hydrogen bonding, to give us an ability to rank them. Now, you may have heard of these things called van der Waals forces. Probably learned about them in biology. They enable, like, geckos and lizards to seem to walk upside down on things. They're kind of London dispersion and dipole-dipole forces put together, sort of, if you will. Questions on our weakest to strongest? All right. So looking at London dispersion forces first. Very weak, and they are temporary. So as you can see in the diagram on the left, these atoms have electrons in them and they're moving around. But at any given moment, all the electrons could be on one side of the molecule, making this left-hand side a partial negative and this right-hand side a partial positive. Well, if two atoms happen to be doing that at the same time and they get near each other, there's an attraction that can occur between the partial positive of one and the partial negative of the other. Now understand this, when this attraction occurs, it can instantaneously go away. It's temporary, it's there, and then it's not. The electrons are constantly moving. So, it's on, it's off, it's on, it's off, it's on, it's off. It's why it's very, very weak. So ultimately, London dispersion forces, or LDFs, caused by a temporary unequal electron distribution that makes these temporary dipoles, which again can call instantaneous dipole, but then it goes away. So it's not permanent. Questions on LDF? Okay. Another example, looking at iodine. An iodine is diatomic. So in order for an iodine molecule to be bonded or attracted to another iodine molecule, the electrons have to move around. Now notice we're not referring to the electrons in this bond. These two electrons aren't going anywhere because it's an equal electronegativity. But all the other electrons can eventually just go one side or the other. Continuing along with LDF, everything has London dispersion forces because everything has electrons. So even though something may have a stronger IMF that controls its bonding and its properties, it still also includes London. Bigger molecules will have more LDFs. There's more surface area. There's more electrons that can move around to invariably give you that temporary unequal distribution. For example, C8H18 will have more or stronger London dispersion force than C3H8. It's bigger. It has more electrons available. Other thing to note, London dispersion forces mainly occur with non-polar molecules and noble gases. Yes, everything is London, but the primary attraction, the primary IMF that uses London and nothing else are non-polar molecules and noble gases. Questions on London dispersion forces? Okay. Next strongest one, dipole-dipole. Only occurs when you deal with polar molecules. So we take hydrogen iodide. Iodine, way more electronegative than hydrogen, gives us our dipole towards iodine. The negative of that molecule, partial negative of the HI, is attracted to the partial positive of a neighboring HI molecule. So, as I said, forgot to hit the button, partial negative attracted to the partial positive of another one, and obviously as you get an entire huge sample of hydrogen iodide, they're all doing this. Questions on dipole-dipole? All right. Oh, there's our attraction, the red dotted line, dash line. Hydrogen bonding. Now, hydrogen bonding is our strongest IMF. But yes, it is also a type of dipole-dipole. So, there's specifics we have to look at. First one, hydrogen bonding can only exist if there is a hydrogen that is bonded to nitrogen, oxygen, or fluorine. If hydrogen is bonded to some other element other than nitrogen, oxygen, fluorine, it cannot be hydrogen bonding. So it's very specific. So we look at two water molecules. The electronegative of one water molecule will be attracted to the electropositive side of another water molecule. Notice this hydrogen is bonded to an oxygen. So, what attraction are we looking for? The partial negative part of a lone pair on NO or F. So this oxygen here actually has two lone pairs. And then the hydrogen end of another molecule where that hydrogen is bonded to nitrogen, oxygen, or fluorine. Questions on hydrogen bonding? Okay. So, lovely little chart. Start off, is the molecule polar? If it's not polar, it's London dispersion forces only, as we alluded to earlier. If it is polar, then we got to figure out, well, does it have any hydrogen bonded to NO or F? Then you can choose dipole-dipole, or if it does, then you can choose hydrogen bonds. Our goal here is choosing the strongest type of IMF that exists. Questions on this chart? Okay. So, properties. Always want to get into properties. How does bonding affect properties? Well, here we have, big thing of water molecules, and they're all attracted a little bit differently. The electronegative end of one water molecule attracted to the electropositive of another one, and then you obviously build this out into an entire sample of water. So, boiling point, melting point, viscosity, surface tension, all of these things are going to go up when you have stronger IMFs. So, if you're comparing a bunch of things based on boiling point, figure out the IMF that exists between everything. Higher the boiling point has to be stronger the IMF. Miscibility, dealing with mixing, still comes down to our saying of like dissolves like. So put a polar thing with a polar something else, they're going to mix with each other. put a nonpolar thing with another nonpolar thing, they're going to mix with each other. You put polar and nonpolar together, nothing's going to happen. Oil and water. You can mix them in a blender for an hour. The minute you turn the blender off, all the oil is going to rise to the top. So, gotta be similar in their bonding characteristics in order for them to actually mix. Questions on properties? All right. All right, special examples of IMFs. One pertaining to hydrogen bonding. DNA. Should have all remembered this from biology. We know how DNA is held together. It's all hydrogen bondings. A to T, C to G. They all use hydrogen bondings to hold them together. Here's those hydrogen bondings, or hydrogen bonding pairs. We can see here this oxygen has lone pairs. This hydrogen is connected to a nitrogen. This nitrogen has a lone pair. This hydrogen also bonded to a nitrogen. Same idea with our GC. All of there's a lone pair existing, as well as a hydrogen bonded to NO or F. There they are highlighted for you. But you should know this because you guys already took biology. Now, proteins, again, also having to do with inside the body. When you get to secondary structures and tertiary structures, beta sheets, alpha sheets, different ways that proteins are put together to ultimately make, for example, hemoglobin. A lot of stuff going on here. But again, it's just a crap ton of hydrogen bonding. Excuse me for saying that, but it is. All right, another type of bond, if you will, deals with bulk solids. So the interaction of solids ends up being a kind of a combination of intra and intermolecular forces when you deal with, again, large or bulk scale of things. Three types dealing with metallic, ionic lattice structure, and network covalent to give them a ranking. These things have extremely high properties, melting points, boiling points. There are so many interactions, both intra and intermolecularly, that give it amazing strength. So, ionic lattice, these are basically ions stacked in an ordered fashion to form crystals. So it's kind of a crystal structure where it has a repeating pattern over and over again. The pluses are the sodium, the green ones, negatives are the chloride, as an example. Here's, salt crystals. It's very, very strong because there's a lot of positives attracted to a lot of negatives. Metallic ions, again, interestingly, also form a type of crystal structure. But again, we have that whole sea of electron idea where all these negative electrons are free-flowing through everything, all attracted to the nucleus or the protons of everything, makes metals pretty darn strong. Questions on ionic or metallic? Okay. Network covalent. This is our strongest one, where everything is covalently bonded through an entire network of bonds. Biggest example, or most known, was going to be carbon. On the left, we have diamond, where every single carbon is tetrahedrally bonded to 4 other carbons. On the right, we have graphite. That's stuff that you write with in pencils. So, an individual graphite sheet, extremely strong. But if I go one sheet to the next sheet, it's just going to be London dispersion. That's what allows you to write with pencil lead, which is called graphite, not actually lead. You're leaving sheets of graphite on your paper. Very easy to break. But the individual sheet itself, you're not breaking that one. Every carbon is trigonal planarly bonded to 3 other carbons. So everything is connected. Questions on network covalent? All right. So our overall ranking of everything, the 3 on the left are your intermolecular forces, London dispersion, dipole-dipole hydrogen bonding, and then you get to bulk solids, metallic, ionic, and then network covalent. So if you had a mixture of all these things, you could then rank them strongest to weakest. You could rank them on properties, melting point, boiling point, things of that nature. Questions on the overall ranking of this? Okay. Alright, let's see if this one's going to work. Yes, I wanted to watch this.
It's midnight, and all is still, except for the soft skittering of a gecko hunting a spider. Geckos seem to defy gravity, scaling vertical surfaces and walking upside down without claws, adhesive goos, or superpowered spiderwebs. Instead, they take advantage of a simple principle, that positive and negative charges attract. That attraction binds together compounds like table salt, which is made of positively charged sodium ions stuck to negatively charged chloride ions. But a gecko's feet aren't charged, and neither are the surfaces they're walking on. So, what makes them stick? The answer lies in a clever combination of intermolecular forces and structural engineering. All the elements in the periodic table have a different affinity for electrons. Elements like oxygen and fluorine really want electrons, while elements like hydrogen and lithium don't attract them as strongly. In atom's relative greed for electrons, it's called its electronegativity. Electrons are moving around all the time and can easily relocate to wherever they're wanted most. So when there are atoms with different electronegativities in the same molecule, the molecule's cloud of electrons gets pulled towards the more electronegative atom. That creates a thin spot in the electron cloud where positive charge from the atomic nuclei shines through, as well as a negatively charged lump of electrons somewhere else. So the molecule itself isn't charged, but it does have positively and negatively charged patches. These patchy charges can attract neighboring molecules to each other. They'll line up so that the positive spots on one are next to the negative spots on the other. There doesn't even have to be a strongly electronegative atom to create these attractive forces. Electrons are always on the move, and sometimes they pile up temporarily in one spot. That flicker of charge is enough to attract molecules to each other. Such interactions between uncharged molecules are called van der Waals forces. They're not as strong as the interactions between charged particles, but if you have enough of them, they can really add up. That's the gecko's secret. Gecko toes are padded with flexible ridges. Those ridges are covered in tiny hair-like structures, much thinner than human hair, called setae. And each of the setae is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do: stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness, but a gecko has about 2 billion of them, creating enough combined force to support its weight. In fact, the whole gecko could dangle from a single one of its toes. That super stickiness can be broken, though, by changing the angle just a little bit. So, the gecko can peel its foot back off, scurrying towards a meal or away from a predator. This strategy, using a forest of specially shaped bristles to maximize the van der Waals forces between ordinary molecules, has inspired man-made materials designed to imitate the gecko's amazing adhesive ability. Artificial versions aren't as strong as gecko toes quite yet, but they're good enough to allow a full-grown man to climb 25 feet up a glass wall. In fact, our gecko's prey is also using van der Waals forces to stick to the ceiling. So, the gecko peels up its toes and the chase is back on.
Alright, hope you guys liked that one. Alright, this last one having to do with liquids. Not going to watch it today. You guys can watch this one on your own to kind of see a little continuation of IMFs and how they work regarding liquids. So please do check that out, and we will go from there. Thank you very much.